Hello, welcome to Forvist Academy. We are going to look at the Friar contest in this video. So that is the contest for grade 9 students, and full solutions are required in this contest. It's not a multiple choice contest. We have 75 minutes to complete the whole contest, but I think we are going to finish this much sooner. These are just the general instructions. This one comment says to express answers as exact numbers. So pi plus 1, for example, is an exact number. We don't have to say 4.14. All right, so without further delay, let's get that time started, and we will try to beat the 75-minute time limit. Okay, let's get started. Question 1. Azizi sold chocolate bars from Monday to Friday over 3 weeks. During the first week, he sold the following numbers of chocolate bars: 15 on Monday, 23 on Tuesday, 18 on Wednesday, 15 on Thursday, and on Friday, 7. Let us see how many chocolate bars did he sell in total during the first week. So we can just say total equals 15 plus 23 plus 18 plus 15 plus 7 equals 78. My math is correct. 38, 56, 61, 71, 78. Okay. And then this is A. And for question B, during the second week, he sold the following numbers of chocolate bars. He sold a total of 73 chocolate bars during the second week. What is the value of X? So this is 22. With that makes 45. So 2X plus 45 is 73. 2X equals 28, X equals 14. Okay. Okay, so X is 14, we can say for B. And during the third week, part C, he sold Y chocolate bars on Monday. Each day from Tuesday to Friday, he sold 6 more chocolate bars than he sold on the previous day. He sold a total of 100 chocolate bars during the third week. Determine the value of Y. Okay, so you would write your solution, a nice clean paper, but being limited on space, I'm just going to write my solution up here. So I have 100 is equal to the sum of, so we have Monday, Tuesday, Wednesday, Thursday, Friday. So he starts off at Y, and then he does Y plus 6, and the next day it's Y plus 6 plus 6, and we carry on like that. Is 5Y plus 60. This is equal to 100. So 40 equals 5Y. Y equals 8. Okay, so that's all there is. That was not too difficult at all. And now let's go to question 2. 3 players, Ava, Bo, and Kato, are playing in a tournament. Each person plays exactly 2 games, 1 game against each of the other players. If a game ends in a tie, both players are awarded 1 point. Otherwise, the winning player is awarded W points and the losing player is awarded 0 points. For example, if the tournament results are as shown below and W equals 2, then points are awarded as follows. Ava loses to Bo, so she gets 0, he gets 2. Bo and Kato tie, they both get 1. Ava and Kato tie, they both get 1. Suppose S is equal to the sum of the points that have been awarded to the 3 players when the tournament has finished. In the example above, Ava is awarded 1 point, Bo is awarded 3 points, and Kato is awarded 2 points. So S equals 6 in the example. Okay, suppose the tournament results are as follows. Ava and Bo tie, Bo loses to Kato, Ava and Kato tie. If W is 3, what is the value of S? Okay, so going back to the example above, Ava is awarded 1 point, Bo is awarded 3 points. and Kato gets 2, so the total is 2 plus 3 plus 1, 6. So S is the total, and if we get, okay, let's say Ava, Bo, Kato. So in the first game, Ava and Bo tie, Bo tie. Bo loses to Kato. So Bo loses, he gets 0, and Kato is going to get 3. And then Ava and Kato tie. So what is the value of S? So we got, so for every tie, we get 2 contributed to S. So 2 plus 2 is 4 plus W. So S is 7. 2 times 2 plus 1 times 3 equals 7. Okay, and if W equals 4 and S is 6, how many games end in a tie? So we know that S is equal to 2 times the number of ties, we said that before, plus the number of wins. And the number of wins is equal to, let's just assume it's 1. So then T would be 1. Okay, the problem here, if only one game ended in a tie, 2 games would have ended in a win. But then the total would have been, so if we're assuming this, the number of ties must have been 2 because there are 3 games. And this is equal to 8. Okay, that's not equal to 6. And if the number of wins was 2, there was 1 tie. And we have 8 plus 2 is 10. That's no good. And if 3 wins, the S would be 12. So there must be 0 wins and 3 ties. Okay, and then S is 6. Another way we could have written this is the following. 2T plus 3 minus T times W is equal to 6. So then we get 2T minus 4T is minus 2T, and then 3 times 4 is 12 minus 2T equals 6. So we get 6 equals 2T, T equals 3. 3 games end in a tie. Suppose the tournament finishes with exactly one of the 3 games ending in a tie. If S is 24, what is the value of W? Okay, so then we have 1 game ends in a tie, 2 games end in a win, and this is equal to 24, so W equals 11. Okay, suppose the tournament finishes with S equals 21, but we're not told the results of the games. Determine all possible integer values of W. Okay, so then we're going to have that 21 is equal to 2 times T plus 3 minus T times W. Okay. So T can be 0, 1, or 2, or 3. And let's solve for W. We get 21 minus 2T over 3 minus T. This is W. So plugging in T is 0. We get W is 7. Plugging in T is 1. We get 19, which is prime. It's not going to give any integer when divided by something. Plugging in T is 2. 21 minus 4 is 17. Again, is prime. And 21 minus 2 times 3 is 21 minus 6. That's 15. And if we divide by 0, can't do that. Can't do that. So I think that's is the only answer. So just giving this a once over, we tried 21 minus 0 over 3, which worked. We did 21 minus 2 over 2, which didn't work. We did 21 minus 4 over 1, which didn't give us integer, and we did 21 minus 6 over 0, which didn't work. So we only got one possible answer. If S is 21, the only possible integer value for W is 7. Okay, so that is all for question number 2. Now let's go on to question number 3. Okay, prime factorization of 784 is 2 times 2 times 2 times 2 times 7 times 7, or 2 to the 4 times 7 squared. And so 784 is a perfect square because it can be written in the form 2 squared times 7 times 2 squared times 7. The prime factorization of 45 is 3 squared times 5, and so 45 is not a perfect square. However, 45 times 5 is a perfect square, since 45 times 5 is 3 squared times 5 squared equals 3 times 5 times 3 times 5. What are the possible integers j if j is less than or equal to 20, for which 2 cubed times 3 squared times j is a perfect square? Okay, so we got the following then. We know that 2 cubed times 3 squared times j, this is equal to 2 squared times 3 squared times 2j. And j is less than or equal to 20. So this is already a perfect square. So we just need this to be a perfect square. So let k equal 2j. Get all k positive, so greater than 0 and less than or equal to 40, such that k is a perfect square. So we're basically, we want k can be 1, 4, 9, 16, 25, 36. And then which one of these are even? Only those are even can be divided by 2. So then j can be 2, 8, or 18. So these are possible options for j. B, determine all positive integers k so that 20k is both a perfect square and a divisor of 3600. Okay, so if 20k is a divisor of 3600, k would be a divisor of 180, right? Let's think of different ways we could approach this problem. So let's break up 3600. This is 36 times 100, right? Which is 6 times 6 times 10 times 10, 2 times 3, 2 times 3, 2 times 3, 2 times 3. 4. So this is 3600 equals 2 to the 4 times 3 squared times 5 squared. It's 225 times 16. 3 times 5 is 15, and that squared is 225. 225 times 16 is 3600. Okay, so how does that help us? We want 20k. 20k is equal to 2 times 2 times 5k. So we got, this is 2 squared times 5k. But this has to be a divisor of this. So 2 to the 4, 3 squared, 5 squared over 2 squared, 3 squared, 5 over k. So k has got to be a divisor of 2 squared, 3 squared, 5. And it's got to be a perfect square. So what is this number here? This is 4 times 9 times 5, which is 180, right? We want basically k to be a divisor of 180. So what are the possible values of k? So 180 So 180 equals 2 squared, 3 squared, 5. Okay? And 20 is equal to 2 squared times 5. So if I want 20k to be a perfect square, this is what we need to do. The only difference between these factors and this is that this has these 3 squared. And we want 20k to be a perfect square. So the combination of whatever I take from here and what I add to here has to give all even powers of exponents. So I have to take a 5. So k has to be always having 5 times, and then it can have 2 to the 0 or 2 to the 2, 3 to the 0 or 3 to the 2. So there's 2 combinations for exponents of 2, 2 combinations for exponents of 3. So that gives 4 possibilities. So it'll be 5, 5 times 4, 5 times 9. And then I can take both the 4 and the 9, so 180. So these are my possible values for k. Okay, so this was a kind of roundabout solution. Let me show you another solution. So 20k is a square. And k has 5 as a factor. How do we know k has 5 as a factor? Because 20 is 2 squared times 5. And we know 20k is square. So we must have k must be having a factor of 5 to make an even powered on this 5, right? So let k be 5j. Okay, then we have 20 times 5j equals 100j. And this must be square. It must be square, and it must divide 3600. So j could then be 1, it could be 4, it could be 9, it could be 36. Because 100, 400, 900, and 3600 divide 3600. So then k could be 5, 20, 45, and 180. Okay, that's another way to do part B. Now from part C, determine the number of ordered triples of positive integers a, b, c so that a squared, b squared, c equals 2025. So we know that 2025, let's write this as 25 times, it's actually 25. I just want to quickly jump to the answer here. So this is going to be 8, 200, remainder 25, 81. So 80 times 81, and then we have 5, 5, 9, 9, 3, 3, 3, 3. So this is equal to 3, 4 to the 4, 5 squared. Okay, so it's equal to 3 to the 4, 5 squared. So we have a squared. Let a equal 3 to the x1, 5 to the y1. B is 3 to the x2, 5 to the y2. And c equals 3 to the x3, 5 to the y3. A squared is going to be this, b squared is going to be this. So then our equations would be this all multiplied together would give 3 to the 4. This all multiplied together would give 5 squared. So putting that together, we have 2x1 plus 2x2 plus x3 equals 4, and 2y1 plus 2y2 plus y3 equals 2. So for x1, x2, x3, we'll end up having these combinations. That's 6 combinations, and for y1, y2, y3, we will have these combinations. So we have 6 combinations times 3 combinations. They can be assigned independently. So there would be 18 ordered triples. A, B, C satisfy that condition. You can choose any row here and any row here, and choose your exponents to assign values to A, B, and C. Let's just try these circled ones. So if x1 is 0, then A is equal to A squared is equal to 3 to the 0, which is 1, and then 5 to the 0, which is 1. B is equal to 3 to the 2 times 2, 3 to the 4, which is 81 times 25, and then C is just equal to 3 to 0 times 5 to 0, which is 1. So that works because this is 2025. So that's an example of how you could use one row from this table and one row from this table to assign values to A, B, and C. And there's 18 combinations. All right, on to the last question. Parallelogram ABCD has vertices 0, 0, 7, 0, 9, 4, and 2, 4. Let's draw that. 0, 0, 7, 0, 9, 4, and 2, 4. Point E, 4, 4, lies on CD. What is the sum of the areas ABC? So this is A, B, C, D. What is the sum of the areas of triangle ABC? So this ABD, so ABD and ABE. Okay, what is the sum of that? So the sum of this, well, this is half of the triangle. So the triangle, what's its area, length times height, which is 7 times 4 is 28. This shaded area is half the triangle. Notice that, or half the parallelogram. So this is 14. Notice that this is also half a parallelogram. Okay, so this is 14, this is 14. And now ABE, the height of the triangle is the same as the parallelogram. The base is the same. Base times height over 2 is the area of the triangle. So the area is therefore 14 plus 14 plus 14, which is 42. Okay. Notice I'm not showing full solutions, what you have to write. I'm showing you how to get the answer, but it's up to you to to write something like triangle ABC plus triangle ABD plus triangle ABE equals area ABCD times 3 over 2, right? Which is equal to 28 times 3 over 2 equals 42. And you might want to show diagrams to show how you established that each triangle had an area of half of the parallelograms. Let G be a point with integer coordinates that lies on the perimeter of ABCD. Suppose CDG has non-zero area. So let's just clean this up a bit. Okay. Okay, so CDG. So G is not on here because that would give a triangle with zero area. So G is somewhere here, here, or here. Okay. How many possibilities are there for the point G? So G could be here, it could be anywhere down here, or it could be here. So there are 8 points along the bottom. X could be 0, 1, 2, 3, 4, 5, 6, 7, and this and this. So that gives 8 points plus 0, 1, 2, 3, 4, 5, 6, 7. That's 8 plus this, 10 possibilities. Determine the sum of the areas of all triangles whose vertices all have integer coordinates and lie on the perimeter ABCD. Okay, this is very case-based question, you could say. We're going to have to look at a lot of cases. So let's say our triangle has a base on the top, okay? So this is going to be quite a long question, but we'll try to solve it in the most elegant and streamlined fashion as possible. So let's assume case one. Case one, triangle has base on DC. So the base could be having a length 7, 6, 5, 4, 3, 2, or 1. If it has a length 7, there's only one way for that to happen. If it has a length 6, it could either start at 2 and end at 8, or start at 3 and end at 9. So there's 2 ways it can have a base of 6. Similarly, 3 ways it can have a base of 5, 4 ways it can have a base of 4, and so on, right? So 6 ways it can have a base, 7 it can have 1, right? If it has a length of 1, it could be 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 7 to 8, 8 to 9. So the total length of the base interesting numbers here. Okay. This is 19, 19, so 38 plus 30, 68, 84. That could be the base. And if another way we could have written this is 7, 6, 6, 5, 5, 5, 4, 4, 4, 4, 3, 3, 3, 3, 3, 2, 2, 2, 2, 2, 2, 1, 1, 3, 4, 5, 6, 7. So we could have said this is that's 28, and then 21, 15, 10, 6, 3, 1. And if we totaled it that way, this is 20, 35, 56, Yeah, 84. Okay, just checking the arithmetic. So if you're convinced that the total length of bases you could have along the top are 484, then we can touch down to this point, or any of this point or this point. So then 1.1, we could say uh, vertex D is a point. So the total area of those triangles is 84 times what's this point? This is 1, 2. Okay, it's halfway between here and here. So the height is 2. 84 times 2 divided by 2. That's the total areas, total of all the areas of those triangles. Now vertex B, same thing. The height is still 2. So 84 times 2 over 2. And if the vertex 1.2, vertex on AB, there are 8 vertexes we have, and the height is 4. So we have 84 times 4 over 2, but we have to multiply the 8 different options. So this is equal to 168, and the total here is equal to 84 times 16. What is that equal to? 250. Okay. Yeah, so now we can the total of this. What is the total of that? 1512. We could just as easily have had the triangle have the base on ace B, and we will still get 1512. Everything's just upside down. And okay, so we're up to 3024 for our area. And now, what if case 3, so remember this number, 3024, and case 3 is that we have, well, there are actually a lot more cases. We could have our base here. Let's call this E, and this F. Case 3, base is E or F, EF. Then we can have our vertex at any of the 8 on the top or any of the 8 on the bottom. So we have 16 possibilities. So then the total area is equal to the base, which this length is 7, times the height. The height is 2, divided by 2. And how many such triangles are there? There's 8 on the top, 8 on the bottom. So this is equal to 70 plus 40 to 112. Okay, so we can add a 112 to that. In case 4, now this is a tough one. Base between top and bottom. So you could have like vertex here and a vertex here, and then we're touching either this, either F or E. So here we have to use something called the shoelace theorem. First of all, let's label this nicely. Okay, so let's say that this is x1 and this is x2. And let's choose this point F and then vertex at F. So then we have, using the shoelace theorem, this is x1 0, and this is y2 4. So we have, let's list the vertices going clockwise. Okay, shoelace theorem, and you list the last vertex again. You multiply the x of one coordinate times the y of the other, and then you add x times the y of the other, that's 0, x times the y of the other, plus 2, x1, and then you subtract the y times the x of the next, y times the x of the x, well, y times the x of the next, this is 0, and then you divide by 2. So we get 4 minus 2x1 minus 2x2 over 2, and this is equal to 2 minus x1 minus x2. Okay, and choosing x1 from 0 to 7, and choosing x2 from 2 to 9, let's see how many values this can take on. This seems tough, but we're almost done, so hang in there. After we figure out this, we just have case 5, which is the same as this, but we have vertex at E, and it's going to have the same answer as case 4. So then this is going to, our area is going to about, let's say x1 is 0. So x1 is 0. Now let's evaluate 2 minus x1 minus x2. So that's just 2 minus x2. So this is going to take on values of, depending on these, it's going to be 0, -1, -2, -3, -4, -5, -6, -7. Yeah. So we have 8 values. So there's 8 values here. And then for every time x1 goes up by 1, this whole thing is going to go down by 1. So this would be negative. And then the area is actually positive, so we can take these to be positive. So 0, 1, 2, let's write it up here, 0, 1, 2, 3, 4, 5, 6, 7. And then for every value this goes up, the magnitude of this is going to go up by 1. So then this is 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10, 11. So we've done 1, 2, 3, 4, 5. But 3 more to go. 5, 6, 7, 8, 9, 10, 11, 12. 6, 7, 8, 9, 10, 11, 12, 13, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so what is the sum of all of this? Notice that the sum of the first column is the numbers 0 to 7, which is 28. And the sum of the next column, since there's 8 numbers and every going one column to next, you just add 1 to every row. So that's going to be 28 plus 8. And we have 3, 4, 5, 6, 7, 8 columns. So the sum of all of this, wait, 1, 2, 3, 4, 5, 6, 7. So in the final column, the sum of this is going to be 28 plus 7 times 8. We take this, we divide by 2, and we multiply by the number of columns. So this is 56 plus 56, which is 112, divided by 2 times 8, so 112 times 4 is 448. We add 448 up there, and then case 5, same as case 4. So we add that again. So our total is going to be 3024 plus 12 plus 896. So this is the answer that we have come up with, 3,932, except, yeah, I almost thought we forgot to divide by 2 for shoelace theorem, but we did not. We remembered it. So I believe this is the correct answer for part 4C. That was a lot of geometry and a lot of cases we considered, but we pulled through it. Okay, I hope you liked this video, and I look forward to seeing you in our next contest video. Thank you. Take care.